lecture 17 today and lecture 18 and 19 later this week. We've got a lot of stuff to do, pretty fundamental stuff. This is kind of what you might call the core of differential calculus. And it includes a review. Here in lecture 17a, we're going to visualize Newton's method again. I'll remind you about that and show you the Mathematica code that Newton's method comes up on with your project. I'm going to talk about the existence of the square root of 2, which sounds like a strange thing to talk about, but I think you'll see what I mean when I talk about it here. Remind you about the infinitesimal calculus applied to the product rule, and look at that maximizing revenue application that we have for the graded assignment today. And lecture 17 will continue with infinitesimal calculus applied to the quotient rule and chain rule. And if we have time, to do some derivative practice as well, and we'll have some time for you to work on it. Hopefully, we'll be able to get there. So let's start by reviewing Newton's method. And I think instead of showing it to you on the PowerPoint, I'm going to go right to the Mathematica, and I'm going to write some things on the board as well. Let's see. Yeah, let's write some stuff on the board first. Actually, in the Mathematica, we're going to be trying to estimate something simpler than square root of 20, you might say, square root of 2. Square root of a smaller number, at least. And if you're going to do that with Newton's method, you'd want to find a root of that function right there. So that function's got two roots, plus or minus square root of 2. Okay. Its graph looks like this. It's a parabola opening upward. Again, the roots are negative square root of 2 and positive square root of 2. Let me just think about trying to estimate the square root of 2 with the Newton's method picture without using the recursive equation. Okay? Let's just call your initial guess A instead of x0. What's the idea of Newton's method? The idea is to go up to the graph, to that point, A comma f of A, and then find the tangent line equation right at that point. It's got slope equal to f prime of A. It's the tangent line there. And you notice it seems to be the case that the tangent line has an x-intercept that's pretty close to the root. Maybe even closer than I've drawn it here. So hopefully that x-intercept would be a good guess for square root of 2. A good approximation. The tangent line has equation in point slope form. Y equals, let's go ahead and write it in the general form first. Say y0 plus m times x minus x0. There's your general point slope form. But what is y0? It's the second coordinate of that point, right there, f of A. x0 itself is A. A is the same as x0 here. It's the first coordinate of this point that we know. It doesn't really look like a point coordinate. It's A. And what's the slope? It's the derivative. F prime of A times x minus A. There's the equation of the tangent line in abstract form. Now find its x-intercept. Set y equal to 0 and solve for x. Set y equal to 0 and solve for x. We did this last time on the PowerPoint screen with subscripts. Let's do it on the board here with no subscripts. Solve that equation for x. It's not as bad as it looks. There's just a number. Subtract it from both sides. It cancels on the right, and you get negative f of A on the left. That's just a number. F prime of A is a number. Divide both sides by it, assuming it's non-zero at least. you get this. A is just a number. We're trying to solve for x. Add a to both sides. X is going to be a minus f of a divided by f prime of a. That's the x-intercept, as long as f prime of a is non-zero. If you think about it, if f prime of a was equal to 0, then you'd have a horizontal tangent. It would not have an x-intercept, unless it was on the x-axis itself already. Newton's method equation is to iterate this expression right here. And the subscript notation xn equals xn minus 1 minus f of xn minus 1 divided by f prime of xn minus 1 just emphasizes that we are using this equation over and over and over again. It's called a recursive equation. We use the first one, n is 1, based on a seed and initial guess x0. Then we use it when n is 2, based on the value of x1 we just found, etc. Okay? We are iterating. The project is about iterating functions partially in Newton's method, in the Newton's method situation. The main bulk of the project is not about Newton's method. Come back to the Mathematica here. I did copy and paste the Newton method, NewtonPlot code from the project here. What in the world is this? This is just code you enter. It's code I wrote. I'm not claiming it's the most ideal code. That is generating a new function in Mathematica, a very complicated function that essentially is a program that makes a graph relevant for Newton's method based on some function like x squared minus 2. How do you use it? Once you've entered it, then you use it by typing NewtonPlot, capital N, capital P, using square brackets like you see here, and using this kind of syntax. I didn't really need the x and the y there. I put them there just to emphasize. What I'm doing is I'm applying the NewtonPlot to this function. X goes from, well, I picked 0 to 2.8 here because the square root of 2 is close to 1.4. This is centered on 1.4. Y goes from negative 4 to 4. This number is the seed. 2 is my initial guess. That's x0. 6 is the number of iterates. By the way, when you use this in the project, I would recommend not going past 6. It tends to stall once you go past 6. And then 20 is the number of places of accuracy in our estimates. And when you enter this, you get some numbers and you get a picture of the NewtonPlot. These numbers up there are the approximations that you get from applying Newton's method to estimate the square root of 2. 2 is x0, 1.5 is x1, 1.416 repeating is x2, 1.414, 2.15, blah, blah, blah is x3, then this is x4, this is x5, this is x6. And you can see by the time we get to x5 and x6 to 20 places after the decimal, it's already the same number to that many places. We started with 2, we went up to the graph, made the tangent line, found the x-intercept of that, that's 1.5. Do it again, go up to the graph, down to the line, take the tangent line there, find its x-intercept, that's the 1.416 repeating. And technically speaking, the graph is continuing to do that, though you can't see it anymore. I did modify the code, I call it NewtonPlot without numbers here, to make an animation without the numbers, just the graph, that allows us to zoom in on that route. And we can see as we go further and further in, we will see a point where you see the next iteration here again. We get really close, you can see it there now. Okay, and there's another one, and another one. Okay, I think I forgot I did 6 iterations or something. As you zoom in closer and closer to the true root. That's what's going on. And the graph, you see local linearity here too. The graph looks straight. The tangent line is practically on top of the graph. Not exactly, but almost. And so actually, as you zoom in closer, because of local linearity, Newton's method works better and better. You just get very high accuracy with very few iterations. It's a very effective method. This does beg a little question, though, that I have for you. Does the square root of 2 exist? What do I mean by that? Well, square root of 2, you should have learned in the past, is an irrational number like pi. Its digits go on forever and ever without a repeating pattern. To emphasize that, we can make a manipulate of those digits. There they go, forever and ever and ever, without a repeating pattern. I went up to 1,000 digits here. Here's 20 digits. Can you imagine squaring such a number? Say with the one with 1,000 digits. And it doesn't even equal square root of 2. It's only approximately square root of 2. Anytime you truncate it, make it a finite decimal approximation, it doesn't equal square root of 2 exactly. Who could possibly square such a number to confirm you get 2 when the digits go on forever and ever without a repeating pattern? Nobody in the world knows the Google digit of square root of 2. It's theoretically possible to find out, but nobody knows it. So how do you really know it exists? If you try to actually square this number, for example, as a fraction, say, you don't get exactly 2. You get very, very close, but not exactly 2. That should make my question about does square root of 2 exist seem a little bit more reasonable, like a reasonable of a question to ask. Who wants to square an infinitesimal? How do you possibly do that? How do you even know that the digits are well defined? And actually, if you know about alternative decimal representations, they're not always well defined. Well, proving it exists is difficult. Before I mention how to do that, let me just say that if it does exist, it's not rational. It is an irrational number. And that has actually a very short proof. It's right here. Hang with me here. Follow this argument. If the square root of 2 was rational, if it equaled p over q, say in reduced form, which you can always do, right? With fractions, you can always reduce them. For example, 12/21 can be reduced to 4/7. You can always reduce fractions, so you could always go ahead and assume that your fraction here, if it existed, is in reduced form. And that would be, in particular, either p or q is odd. They couldn't both be even, because then you could reduce it further. Well, what does it mean to be square root of 2? It means if you square it, you get 2. So this would be true. That's what square root of 2 means. Do a little rearranging, and you get this equation. Think about that equation for a second. You realize, p squared is 2 times q squared. P and q are whole numbers. I guess that means p squared is even, because it's 2 times some other whole number, right? That's what even numbers are. I said p or q is odd. I've just concluded p must be even. Say 2 times r. But then you do a little bit more algebra, and you get that q squared is even, and therefore q is even. What? Feels like we're going in circles here? What? What do we conclude? This is called a logical contradiction. And what it means is your error, so to speak, was in the original assumption that square root of 2 could be written as a fraction. It is a logical contradiction. I can always reduce fractions. That means either p or q is odd. But here, after this algebra, I concluded that both p and q are even. That can't happen. It's a contradiction. So the problem's right here. And therefore, square root of 2 must not be a rational number. We call it irrational. This was so groundbreaking when somebody first thought of this, back around 500 BC or so. One of the Pythagorean people, there's Pythagoras, of the Pythagorean theorem. There were also the Pythagoreans, people who followed Pythagoras. And rumor has it that the person who discovered this, they were so upset about it that they killed him. It's story is that he was thrown overboard. Okay, nobody knows for sure if that's true. But it's a story emphasizing how amazing this was to them. That there were numbers that were not fractions, ratios of whole numbers. They didn't know about irrational numbers before something like this happened. So if it does exist, it's not rational. Proving it does exist, well, we're not going to do that. It's a task for the advanced proof-oriented class called real analysis, which we do teach here at Bethel for math majors. Okay, sometimes physics majors take it. Okay, it's a proof-oriented class, like with epsilons and deltas. We don't do epsilons and deltas just for fun. Those, some people like me have fun with them. We do it because it's necessary to prove things rigorously sometimes. It's a necessary thing, and there are issues. Like weird things can happen in math, like those infinitely oscillating functions. Weird things can happen, so you need airtight arguments for things. It's based on something called the Completeness Axiom, which I'm not going to get into, but a class called real analysis proves that square root of 2 exists. It is an issue, but it's a subtle issue. Okay? If you're somebody who's intrigued by that, what I just told you about the square root of 2, then maybe you have a little mathematician. Okay? Doesn't mean you necessarily need to be a math major, but if it intrigues you a little bit, then you have a little bit of mathematician in you. If it doesn't really intrigue you at all, then maybe you don't have much mathematician in you. Okay? And that's okay. You know, God made us all different. He's given us different skills and different things that we like. Okay? We are all different. He wants us to try to develop our skills in areas even if we don't like those areas, because it's beneficial for us. Even if you don't use calculus on the job, you may want to teach your child someday about calculus because you want opportunities for them, or maybe because they like math, if nothing else. Okay? We can all get better. All right, let's move ahead to another slide here. All right, this was the slide that I skipped. I went over it very fast last Friday. The product rule derived with infinitesimals and a bit of ingenuity. I want to go through it more slowly now. These infinitesimals, again, are not rigorous math, at least the way we're approaching it. It's intuitive math. But we're okay with that. We want to be okay with it. Even if you are a math major, a couple of you are, we can be okay with the infinitesimal approach, even though it's not rigorous. For those of you who are not math majors, which is most of you, this is the intuition that is most useful for you outside of this class. In, for example, reading a physics textbook, understanding how physicists think about things, and deriving equations, like laws of motion, laws of electricity and magnetism, and that kind of thing. This is the kind of thing that's most useful, the most useful abstract topic for us. Let h of x be the product f of x times g of x, and think about nudging x by dx. Okay? Move it an infinitesimally tiny amount. Then f and g individually are going to get nudged by a certain amount. Call their nudges df and dg. What is the nudge to dh? What is the nudge dh to h? So we're being it's a little weird because we're using the d symbol now in front of the function names instead of with variables. Now I could bring variables into play, but it would make it even messier. So we need to be okay with using the d in front of the function names. It does represent small changes in their outputs. Well, it turns out to be nicest if you think first about what h plus dh would be. Not just dh itself, but the function output at x plus the little nudge. What is h? H is the product of f and g. So to find h plus dh, we take the product of f plus df and g plus dg. Go ahead and multiply that out. FOIL it. First times first is f times g, that's that. Outside times outside is f times dg, that's this. Inside times inside is g times df, that's this. And last times last is df times dg, that's this. Let's FOIL it. But h equals f times g. In other words, h of x equals f of x times g of x. The x is kind of behind the scenes here. You don't see it up there, it's behind the scenes. Therefore, we could cancel the h and the f times g from both sides. And we have a formula for dg, or dh. Like that. Just cancel. The h canceled with the f times g. Right? These two things here and here are the same. Cancel. You know, if they're both 5, cancel the 5 in both spots. What are we after? Well, okay, this is dh in terms of df and dg. We're after dh dx, right? The derivative of h with respect to x. We are going to divide both sides by dx here. But before we do that, let's use our ingenuity. And the ingenuity is df dg is unspeakably small, lol, so ignore it. Just delete it. You're like, wait a minute, how can I do that? How can I just make it go away? You can in this intuitive math. This is not rigorous math. It's so small, it's unspeakably small. Okay, you know, df and dg individually are infinitesimally small. You multiply them, and it's unspeakably small. So small, let's just treat it like a 0. And not even bother putting approximately equal to signs in there. Keep them equal signs. It's not rigorous math. When I was in your shoes, it just bothered me when my teacher did that. I was like, wait a minute, you can't do that. But then as I've gotten older, I've been like, okay, let's just be okay with it. And it is kind of fun, right? Instead of having to write the limit signs all the time, isn't this more fun? In a way? Even though you don't quite get it? Now divide everything by dx. And if I want to be a little bit more precise with my notation, now let's put the x's in there with function notation like that. There's the product. X is behind the scenes in all of this, okay? H, f, and g all depend on x. They are functions. Get a bit more precise, I can write this. In the 3 blue, 1 brown video,
how do you get rid of one of the df and dg's?
That's a good question. And that's the thing that feels extra confusing about it, I think. You're asking about this, right?
Yeah.
Yeah, that's because it's just so small compared to even these. That's why I'm using this phrase unspeakably small, just to emphasize how small it is. So we're effectively taking it to be 0. Even though these are really tiny too. You might say, well, why don't we make those 0? Because then we get the answer 0. That wouldn't make any sense. We want an answer, so we need to use artistic license, you might say, based on experience and what the teacher tells you, to go ahead and make that a 0, but not these things 0. It did bother me when I was in your shoes. Like, you can't do that. I'm saying, well, you can. And it can actually be made rigorous with that non-standard analysis. We're just not doing it here, not here, because it's just too hard. Okay? In the 3 blue 1 brown video, this was said as a way to remember this is left d right plus right d left. Let me put that. In the original function h of x, it's a product f of x times g of x. The left function and the right function. Left d right. I put the letter d in there. Left d right means the left function times the derivative of the right function, plus right d left. The right function times the derivative of the left function. Left d right plus right d left. is the way to remember that, though you actually can switch it around here from the product rule because addition is commutative. It's not going to work with the quotient rule because there's a subtraction of the quotient rule. Let's differentiate that function for an example. F of x equals x times sine x. There's your left function, just an x. There's your right function, sine x. Left d right plus right d left. Left d right, use the d dx notation, plus right d left. I'm putting the d dx's in here to emphasize what's going on, though in practice, to get an answer, you don't have to write them in there. Since the derivative of sine is cosine, this is x times cos x. Since the derivative of x is 1, this is 1 times sine x. You can write those without the dots. X cos x plus sine x. Is it really right? You can check it with your calculator perhaps, if you've got a good enough calculator, or Mathematica. You find this function up here, say, f of x equals x times sine x. Make sure you use a capital S and in square brackets. What's the derivative? F prime of x. There we go. It wrote it in the other order. Remember to use underscores when you first define functions and colon equals. But then once you've done that, then you don't need the underscores or the colon equals anymore. Does it make sense with a graph? Oh, I highly suggest doing that, checking that once in a while. Which one's which? Actually, I think the original function's in blue. Let me just check that here. The original function's in blue here now. The derivative is in red. The derivative gives you the slopes of the original. Here the slope of the blue is positive. The output of the red is positive. Slope of the blue is 0 right there. The output of the red is 0. Slope of the blue is negative in here. The output of the red is negative. Slope of the blue is 0 right there. The output of the red is 0. Slope of the blue is positive over here. The output of the red is positive. The red is the derivative of the blue. I did that very fast, I know. I'm confident you could go through it to double check it. Okay, and yeah, every once in a while, take the time to check that. Make sure it seems right. Let's end lecture A by looking at the problem that you handed in about the revenue. We also looked at the end of class last Friday. Now let's go ahead and bring in the numbers from the problem itself about sales of skateboards. So Q equals F of P is a demand function. Quantity demanded is a function of price. The graph of this function is going to look, well, it's going to be decreasing for sure. As the price goes up, the demand is going to go down. You're going to sell fewer skateboards at higher prices. But they are higher priced, so maybe more money will still come in. You got to look at the revenue function to see that. Revenue is P times Q, price per skateboard times number of skateboards sold. But the derivative of that with respect to P is not equal to Q, because Q is not constant. It's a function of P. It's this product here, P times F of P. So the derivative, dr dp, which, although I'm sort of mixing up my function name with my variable here. Let me do it this way. I mean, that's sometimes okay, but dr dp is f prime excuse me, no, it's not right. Call it something different. G. Is G prime of P, I need the product rule. Left D right plus right D left. Left D right, the derivative of the right function, plus right D left. The derivative of P is 1. You're differentiating with respect to P. So you can write this in a slightly simpler form as P f prime of P plus f of P. You're told in the problem that f of 140 is 15,000. In other words, when your price is $140 per skateboard, you're going to sell 15,000 of them. Of course, this is over a certain period of time, but we don't need to worry about that. Maybe a month or something. And you're also told that f prime of 140 is negative 100. The rate of change of Q with respect to P is negative 100. For every extra dollar, you're going to sell about 100 fewer skateboards. This would be in skateboards sold per dollar charged. Use these pieces of information to figure out if dRdP is positive or negative when you plug in the price of 140. Just plug the numbers in. P is 140, you get 140 times f prime of P, negative 100, plus f of P is plus 15,000. That's negative 14,000 plus 15,000 is 1,000. It's positive. So yes, sell more skateboards. Or I should say raise the price. At least if you only care about increasing the revenue. That could have been negative. This could have been smaller than 14,000. This could be positive or negative. After the break, we're going to look at a graph of this to illustrate.